Hello friends. In this particular lecture, we are going to see how the resolution algorithm it works with the predicate sentences. Now, resolution algorithm with respect to predicate logic algorithm is exactly same. We have already seen this algorithm for propositional algebra. The algorithmic steps are almost same, exactly same. A slight difference is there. That is only because now we are considering predicate logic sentences, and that time we were considering propositional algebra sentences. So let us start. As I've already spoken about this, resolution algorithm is a proof by refutation algorithm. The input to this algorithm are the predicate sentences which have to be in clausal form or CNF. Okay, so in the next slide, we are going to see the steps for conversion of any predicate sentence to a clausal form sentence. Okay, now after this pre-processing step of converting all the predicate sentences to the clausal form sentences, now the resolution algorithm starts. The steps of the algorithm are, okay, first convert all the propositions of the knowledge base to clausal form. So this is mandatory. All the propositions, kindly note, I have used a word called as propositions. Here it should be predicates. Okay, so convert all the predicates of the knowledge base to the clausal form. Okay, now let us assume that alpha is supposed to be proved. Okay, suppose we have to prove that alpha is true, then we have to negate alpha and convert it also into clausal form and add it to the knowledge base. I'm calling the knowledge base as S. Okay, the first step, we have to convert all the predicate sentences of the knowledge base to the clausal form. Knowledge base is S. Second, we have to suppose we are asked to prove alpha, then we have to negate alpha and then convert it to clausal form, and that also you have to add it to S along with the other knowledge based sentences. Third step, we have to repeat the following procedure until either a contradiction or an empty clause is found or no progress can be made. And the sub steps are, suppose this is one clause and this is the second clause. Okay, now you see that predicate P and predicate not P can be cancelled out because not P and P is false. Moreover, any other term or false gives you that term itself. So not P and P will cancel out, and in the second step the resolvent, whatever is remaining, that is alpha or gamma, is added to the S knowledge base. So you have to go on doing this procedure, executing this procedure till either the contradiction is found or virtually no progress can be made. Now, if you cannot proceed, suppose you are stuck at particular step, okay, then two things can happen. Either the way you have solved is wrong, you need to revisit and check, and second, uh, if you are stuck, if you are not getting contradiction, that means whatever you have assumed negated, okay, that happens to be true, your assumption happens to be true, so what is asked to prove is false. This is a rare case. Okay, now in the next slide, as I had promised, we are going to see the steps, okay, for conversion of any predicate sentence to the clausal form. Okay, now students can kindly note, for exam you're going to get paragraph in English or you're going to get some English sentences. The first step, that what you need to do is each sentence you have to convert it in the predicate logic. Now each of this sentence may not be in the clausal form, then each of this sentence you have to convert it into the clausal form, and only then you have to apply resolution algorithm to this converted sentences, otherwise you will not get answer. So let us continue with the steps for conversion to the clausal form. First step, eliminate implication. So we have already discussed, we can use this formula, P implies Q can be written as not P or Q to eliminate implication. Also, I have not mentioned, but even if there are by implications, implies by, that also you can eliminate here itself with the formula P implies by Q can be written as P implies Q and Q implies P. The second step of the conversion is reduce the scope of each negation to a single term. That means if negation is present outside a sub-expression, then that negation have to be substituted to the each term inside the sub-expression. So this is De Morgan's law. Okay, so if negation is outside sub-expression, you just substitute it inside. We have already discussed this. Second, if the negation is outside a quantifier and an expression, so not of this whole thing, what can happen is when negation is applied to a universal quantifier, it becomes existential quantifier and term P will become not P. Similarly, when a negation is applied to an existential quantifier and a term P, existential will become universal quantifier and P will become not P. And finally, in case of double negations, they will get cancelled and you will retain the original term P. So this is the second step of the conversion procedure. Now let us see some examples of this conversion procedure. Suppose you have a sentence was given to you and you have converted the sentence into the predicate form, and this is that crude predicate form which you have. For all x not of this whole thing, Roman x implies Pompeian x and not hate x comma Caesar. Now, is this sentence ready for use by resolution algorithm? No, because there is an implication. So we have to eliminate this implication first. Now, Roman x implies this whole term can be written as not Roman x or this whole term. We will not touch this outside part. Okay, so after applying step number 1, elimination of implication, this becomes the outside term, it remains the same, inside implication is eliminated, so this becomes not of Roman x or Pompeian x and not hit x comma Caesar. That's it. Now I have converted the sentence by applying the first step, elimination of implication. After elimination of implication, if the sentence is still not in CNF, then you have to apply step number 2. Okay, now step 2 is required to be applied if there is a negation which is present outside a sub-expression. So you can see this whole thing is a sub-expression and there is negation outside the sub-expression. So I have to substitute negation inside. So not of not Roman. Okay, so after reducing the scope of negation, after applying step number 2, not of not Roman will become Roman x, or will become and Pompeian x will become not Pompeian x, right? Now you see this is a full one term. Okay. Please notice the green brackets. So negation will be applied first to this entire term, and then in the next step this negation will be also applied to each of the individual terms as follows. So Roman x and we had already seen this negation will be applied to the first term here, it will be Pompeian x and will become or, not hate will become hate, and that's it. So this is what we get after application of step number 2. Now step 3 is to standardize the variable so that each quantifier binds a unique variable. Now just notice this. This is a predicate statement which is there. For all x, p of x, or there exists some x, q of x. as you have rightly pointed out, this is universal quantifier, this is existential quantifier. But the mistake here is that the same variable name is used for the universal quantifier as well as the existential quantifier. While teaching, I have encouraged you not to use the same variable name for any of the quantifiers. Even if there are two universal quantifiers, I have always used two variable names for each of these individual quantifiers. Okay, but sometimes, so if you follow my method, you will not come to this particular situation where two quantifiers will have the same name, variable name. However, for exam, in order to confuse you, if they give this kind of statement, then this step number 3 is applicable. And what is this step number 3? Standardization means, since both quantifiers have the same name, this x, okay, I will rename it to something else. I will call it, let's say, y. Okay, so that the variable names are standardized, so that there is no confusion also. As an example, consider this particular example. Now we had already seen this example in one of the previous videos. Okay, everyone who loves all animals is loved by someone, right? Now notice that y is a quantifier used for animal, and the someone who loves x, for that also I have used y. So there is a sheer confusion here. So such kind of statements require standardization. So what we will do is, after application of standardization step, the same predicate statement now is read like this, where y, its name has been changed to z, y has been changed to z. So now you have three unique variable names, y, x and z. So this is basically standardization. If required, only then you have to go for step number 3, right? Now step 4, moving all the quantifiers to the left without changing their relative order. This is step number 4. For example, if this is a predicate, for all x, p of x, or there exists y, q of y, as you can notice, x is present in the beginning of the expression. However, this y here is declared somewhere in middle of the expression. So this step number 4 is the one wherein this y we will be moving outside the sub expression, okay, without changing the meaning of the sentence. So for all x, y, when I move outside, it becomes there exists y, and then p of x and q of x can be simply put together and the meaning will not change. Okay, so this step of moving all the quantifiers, may it be universal quantifier, existential quantifier, it may be n number of quantifiers, moving all the quantifiers to the left hand side, okay, without changing the relative order of other terms, this step is called as Prinux normal form. Okay, let us see the example. Okay, let's say I'll be taking the same example. Okay, everyone who loves all animals is loved by someone. Now in this example, quantifier x and quantifier y, they are on the left hand side. However, z is declared somewhere in between. So after applying step number 4, z will be simply moved outside the sub expression without altering any of the other terms, and you get this. For all x, for all y, I have simply moved this z here, and other terms remain same, animal y and loves x comma y or loves z comma x. Okay, so this procedure of moving all the quantifiers to the left hand side of an expression is called as Prinux normal form. Okay, please notice this, please remember this, it is called as Prinux normal form. Okay, Step number 5, elimination of existential quantifier. This is a very important step. If at all in your sub expression there is an existential quantifier, then there is a utmost need to remove it or eliminate it, and this process is called as columnization. Okay, now columnization can be done in two ways. Okay, now please notice this: there exists some x such that p of x is true. Okay, now when I say there exists some x, if you already know some of the values of x, if you already know, if in the knowledge base your system knows some values that x can take, you can simply substitute that value c here in place of x, and you can eliminate the existential quantifier. So substituting one particular value, valid value that x can take, okay, and then removing x itself, this is called as column constant. So cx is a column constant. Okay, I will also show an example after this. It will become more clear. Okay, now sometimes substituting this column constant may not be helpful. That time we go for the second one, that's called as substituting this column function. Now you see, in this particular expression, for all x there exists y such that p of x comma y is true. Now in such predicates, the value of y is dependent on the value of x. So you can't simply substitute any value of y like what I did here. Here, the existential quantifier variable x was independent of any other variable, but here the case is different. Because x and y both are involved in this predicate, the value of y will definitely affect the value of x, and that's why y is dependent on x. So in such cases, we have to substitute y with a function of x. Okay, the value that will not hamper the meaning of x, and that function of x, f of x, is called as column function. Okay, so columnization can be done by either substituting the existential quantified variable with a column constant or with a column function. We will understand this better with the next example. Okay, now consider this: there exists some y such that y is a president. Okay, now here suppose I want to remove this y. Okay, and let's consider that we are talking about president of India. Okay, now in the knowledge base of the system, suppose there are already some names of the ex president or present president of India are present in the system. Then if I substitute that y with any of the presidents of India, then still the statement will be true. For example, if the system has variable y, that's a president's variable, equal to Pranab Mukherjee. So if I replace y with Pranab Mukherjee, still Pranab Mukherjee was president of India becomes true. Or suppose Pratibha Patil was also there in the knowledge base. So replacing y with Pratibha Patil, the second value, second constant, which is known to the knowledge base, also will make this thing true, because president of India was Pratibha Patil also. So in both these cases, okay, what we will do is, instead of making a generalized variable here, I will replace a specific value that that variable can take and remove that variable itself. So what we'll do, this can be transformed into president S1, where S1 is a function, okay, that somehow produces a value that satisfies president S1, and hence S1 is called as column constant. Now whenever in exam columnization is required while solving problem, you can simply replace the y or any variable which is to be removed, any existential quantified variable that is to be removed, you can simply replace it with any constant name, say S1, S2, P1, P2, and say that it's a column constant. That is fine. Now another example wherein column function is required. Now see this example. There exists some y for all x such that y leads x. Okay, so which means y is a leader of x. Now assume that this is a condition of your t-comp class. Okay, okay. Let's say for all x, where x belong to x are nothing but they are all of you students of t-comp class of 2020 batch. Okay, then we say there exists some y such that y leads x. Now tell me something, is the value of y, is it dependent on x? Yes. Why? Because a T mechanical student cannot become CR of your class, or B comp student cannot become CR of class. So the value of y should be one of the student from your own class. So y should be function of x. He should be function of x. He should be member of your class only. Okay, one of you, right? So since y is dependent on x, you cannot simply replace y with a constant which I did here, because y is not independent. In such cases, what we do, we write here f of x. That means the value of y is now function of x. So here value of y that satisfy leads depend on particular value of x. Hence the statement is written as for all x leads f of x comma y. Now in both these cases, once you substitute column constant as column function, you can drop this existential quantifier notation. See, it is dropped from here, and this is dropped from here. You can only retain the universal quantifier, and doing this it will not affect the original meaning of the sentence. So this is columnization. The next step is dropping of universal quantifiers. Now this is very pretty simple sentence. Dropping of universal quantifier means if there are universally quantified expressions, you can simply drop it without changing the sentence. So for all x, p of x after dropping quantifier can be just written as p of x. Example, say you have for all x, for all y, for all z, not Roman x or not no x comma y or hate y comma z. Now this statement is already in Prinux normal form. Now, so if you apply step number 6, dropping prefix the uh, universal quantifier, after doing that it becomes this. You see, I have simply dropped x, y, z, but within the sub expressions, within the predicates, I have retained the name as x, y, z. However, I am just dropping these quantifiers from here. So this is something called as dropping of universal quantifiers. Next step, after executing step 1, 2, 3, 4, 5, 6, okay, we have to apply. Okay, apply the formulas. Now we have already seen some 18 number of formulas, okay, in prepositions. So you have to apply whichever applicable formula so that the given sub expression is converted into conjunction of disjunctions into clausal form. And as I've already discussed, what is clausal form? Clausal form is the one in which different clauses are connected with and. And clause is nothing but when different propositions are connected with or, that becomes a clause. This is one clause, this is second clause, and so on. So then you can use different formulas like association, distribution law, and so on, okay, and try to get it into conjunctive normal form. Fine. Eighth step, create a separate clause corresponding to each conjunct. Now once you get this into clausal form, it simply means that this is one clause and this is second clause. Then you can treat this clause as a separate sentence and this clause as a separate sentence. That is what is given in the step number 8. And step number 9, standardize apart the variables in set of opt-in clauses. Okay, this 9th step is very important. Okay, what is this 9th step? Now, for exam, they'll be giving you 5-6 sentences. Okay, what I'm saying is, if in the first sentence, if you have used quantifier, say x, then in the second, third, fourth, fifth sentence, you should not use the same variable name x for any other quantifier. Okay, so this is called as standardizing apart the variables in the set of operand clauses. So no clause should have the same variable name. So suppose in one sentence, if you have variable name as x1, then in the second sentence you cannot have it as x1 again, you make it x2, then in the third sentence x3, and so on. So this standardization over here is across the set of sentences given to you for proving certain result. Okay, so this is something called as standardization, standardizing apart the variables in the set obtained clauses, set of obtained clauses, not in one sentence. Okay, now we will have a combined example to demonstrate step 7 and step 8. Okay, so let's say we have reached this particular thing: Roman X or hate X comma Caesar and not loyal to X comma Caesar. Okay, now is this in CNF? No, it is not in CNF, because this may be a clause, but this is not a clause. Okay, so then how to convert this into clausal form? So what we do is, I treat this particular term as P. This whole term, which is in the red color, I just call it as Q, and this green color term, I just call it as R. So now the expression given above is exactly like this: P or Q and R. Now looking at this, it is very obvious that I can use a distributive law, that is P or Q and P or R. So when I use the distributive law, I get a CNF or a clausal form. Fine. So step 8, so you are going to get this clauses, right? So what I have done is just replace wherever P is there, I replace it with Roman. Wherever Q is there, I replace it with this red color thing. Wherever R is there, I have replaced it with not loyal to. So the first clause that you are going to obtain is this, and the second clause that you are going to obtain is this. What you are doing in step 8 is, you are going to consider this one as a separate clause or separate sentence, and this one as a separate clause or a separate sentence. Okay, that is it. Now before we continue further, remember that although I have shown you 9 steps, okay, it does not mean that every step has to be applied to the given sentence. What you do is, after converting a sentence into English sentence into a clause, into a predicate form, you see which step is applicable, and then accordingly whichever step is applicable, just go on applying in order. It may so happen that one particular step is not required to be applied for this particular expression, so you can skip that and go for the next one. Okay, and so on. Now after seeing the resolution algorithm overview, and also after seeing what prerequisites are required for this resolution algorithm to work, how CNF form can be generated, okay, we will see another important aspect, another important algorithm which is present in the resolution algorithm itself, and that algorithm is called as unification algorithm. Okay, what this unification algorithm does is, in the resolution algorithm, when it is trying to compare two clauses, okay, unification algorithm is a small routine that tries to unify these two clauses by finding out what is common in those two clauses, what is the substitution which makes those two clauses common, so that cancelling is possible. Okay, let's see this further. So what is unification? It is a matching procedure that compares two literals and discovers whether there exists a set of substitutions that can make them identical. So it is basically a matching procedure which compares two literals and then discovers whether there exists a set of substitutions that can make them identical. Example: suppose there is one term hate Marcus comma X, and second term is hate Marcus comma Caesar. Okay, unification algorithm will try to find out what is common in these two. Okay, so it will try to get the substitution called as theta which when substituted both the terms will become same. So the substitution that it is going to do is, it will say that if x is replaced by Caesar, then both these terms can be unified. That means they can be same. So this is the unification algorithm. Second example, suppose I have hate x comma y as one literal, and the second literal is John hate z. They can be unified if and only if, okay, the first substitution theta 1 is such that if x is replaced with John, or if z is replaced with y, if both these substitutions are carried out, then both these terms, literals, can be unified. So in general, how this unification algorithm works? So this is the unification procedure. The subroutine called as unify, it takes two literals or two clauses p and q as input, and as an output it gives unifier theta, okay, which is actually a substitution where, okay, what is that theta? Where substituting theta in p, where substituting theta in clause p or literal p is same as substituting theta in clause q. So that means when theta is substituted in p or q, it will make these two p and q literals equal. Okay, let's see an example. Suppose these are the set of predicates which are given to us. For all x, John knows x implies John hates x. Then next, John knows Jane. Third, for all y knows Leonid. Fourth, for all y knows mother of y. And last, for all x knows Elizabeth. Okay. Now, unification algorithm, we'll try this unification algorithm. We'll give the first term as John knows x, okay, and John knows Jane. Let's say these are the two terms or two literals given. Can they be unified? What will be the substitution? So unification algorithm will say, if x is replaced by Jane, so if theta is this, then both can be unified. So the output given by the unification algorithm will be Jane slash x. So this is the theta given as output if this and this is given as input, right? Next, unify. The first literal given here is knows John comma x. The second input given here is knows y comma Leonid. So unification algorithm will say, if y is replaced by John and if x is replaced with Leonid, then both the literals can be unified. So it will give two substitution. Theta 1 will be x replacing with Leonid, theta 2 will be y replaced with John, which will unify these two sentences. Third, unification algorithm now takes two inputs, knows John comma x and knows y comma mother of y. So here also it will give two substitutions. Both can be unified if y can be replaced with John, here theta 1, and x can be replaced with mother of y, and now y already, since y is John, so it will be mother of John. Okay, so first when it gets theta 1, y has to be replaced with John, so that substitution is already done. So then x, okay, should be replaced with mother of y, but y is already John now, so mother of John. So this is unification. But third one here, unify knows John comma x and knows x comma Elizabeth. Please note, it tries to unify by getting a substitution of x with John. But if x takes the value John, okay, when it tries to go for the second term, x has to now take the value Elizabeth. Correct? So see, the thing is, first time when it sees this x and this John, it tries to get the substitution that, okay, fine, if x can be replaced with John, the first term can be okay. But x is already John now. When it goes second, it sees that x has to be now replaced with Elizabeth. By the time it replaces x with Elizabeth, the value of John within X is lost, and as a result it fails. Okay, so this is the end of today's session. In the next session we will actually work with an example of resolution algorithm. Thank you.